All right, hey everybody. I am going to finish up with the 8.1.2 guided notes with you on this video. So please make sure you have this page out. There are extra copies of this if you were absent last class, as well as the 8.1.1 available on in the corner of my desk. So if you need to grab those yellow worksheets, go ahead and grab those now if you need a copy. Otherwise, get yours out from the other class. You gotta let me do this, okay? Okay, go watch your movie. Love you, buddy. It's one of them. Go sit down. Okay. So last class, we started this section by graphing just these four graphs. So we had figured out by now that if it's in factored form like this, we can figure out the x-intercepts of a polynomial pretty quickly. So if these are my three factors, just like we usually do when we're solving something that's factored, when we set it equal to 0, you just set each factor equal to 0, and then you know where that graph has a y value of 0. In other words, our x-intercepts. We also figured out that if our leading coefficient is positive, then for these fourth degree polynomials at least, that end behavior, they both point upwards. And then if that like in example C, that negative out front means everything's flipped over the x-intercept or the x-axis. So this is kind of where we left off. We're going to continue looking at what information these factored forms of polynomials give us. So before we move on to the next problem, let's look at example E right here. Now this one's a little different because it actually has 5 factors. So this is a 5th degree polynomial. We haven't really worked with 5th degree polynomials yet, but we know enough that we can at least plot the x-intercepts of this. So if x plus 6 is a factor, that means I definitely have a x-intercept of -6. X plus 3 is a factor, which means I've got an x-intercept of -3. X minus 5 is a factor. So 5 is an x-intercept. X minus 8 means +8 is an x-intercept. And x minus 12 means +12 is an x-intercept. So we can at least plot all of these. Now the question is, how do we know where this graph starts and ends? So let me refer back up here to this 3rd degree polynomial. We knew based on our experience with cubic functions that 3rd degree polynomials have this general behavior. They start down here and then they go up. So we knew that we could just adjust our knowledge of that to these zeros and still fill in. So it starts down here, it goes up, and then it ends towards the positive values. So we can take a quick look at what the parent graph of x to the 5th looks like. So I'm plugging x to the 5th to my calculator. I can look at my graph and you'll see that it looks really similar to x to the 3rd. So x to the 5th behaves very similarly. It starts down here and then curves a little bit and then goes up. So we can apply that to this. Now, this means it's going to start down here and it's going to end up here. And in between, it's going to cross through all of those x-intercepts. So we can fill in the rest of that graph right here. So fill in your graph. And this isn't necessarily an accurate graph, but we at least have these ends accurate and where it crosses the x-axis. Okay, so we're going to move on to problem 23, and we're talking about roots of a polynomial. You are going to hear me use the word root a lot when we talk about polynomial. The good thing is we've already been working with, sorry, I think my computer might have just gotten a little glitchy. We've already been working with the concept of roots. We've just been using different words for it. So any time you see an x-intercept, that's a root. So you'll hear me interchange those. They're not always interchangeable, but every x-intercept is a root of the polynomial. And another word you're going to hear me use for x-intercept is 0 of a polynomial. So these values right here, where it's touching or crossing through, we typically call those x-intercepts. That's what you're used to. Another word you've heard me use for those maybe is a zero of the polynomial, because when you plug these numbers in, like if I plug 8 in for x right here, it's going to make the whole thing equal 0, because this factor would equal 0. And then when I multiply by these other factors, everything times 0 equals 0. So x-intercept or 0, these are also called roots. So I will interchange these a lot. They all mean basically the same thing. There's a couple of cases where roots aren't always, zeros aren't always roots. Ignore that, that's not true. Just because, well, there's some other issues in terms of certain types of polynomials when it comes to roots versus, oh, right here. So x-intercepts, sometimes functions don't have x-intercepts, but they do still have roots. So not every root is an x-intercept, but every x-intercept is a root. And if you're confused, just ignore the last 30 seconds. I promise everything will be okay. Okay, so roots of a polynomial are those x values that make the polynomial equal 0 when you plug those x values in. So this is the formal definition. If you plug in a root, it's an x value, it will make the whole polynomial equal 0. For example, check out this polynomial, x minus 4. It's a very simple linear polynomial. What value of x will make this equal 0? That would be 4. That would also be the x-intercept. I would also say 4 is a 0. So this 4, this is an x-intercept. It's a 0. It's a root. So those three things all mean the same thing in this case. So this next one, x minus 4 times x plus 7, if that's my polynomial, then it has two roots, and they're the two values of x that make this whole thing equal 0. So I'm just setting each individual factor equal to 0. It's the same exact thing we did here. So here I was just calling them x-intercepts. These are all roots as well. So this has roots 4 and -7. So this word, we've already been looking at the concept, we just haven't used the term root yet. Okay, so let's talk about maximum number of roots. So how many possible roots? Remember, these are the same things as zeros, values that make the whole thing equal 0. Maximum number of roots that a polynomial of degree 3 can have. Well, let's think about that. A third degree polynomial, this is the parent graph. So this only has one root. What's the highest number of roots that could have? We've seen situations like this already. Right here is a third degree polynomial, and we see it crossing through the x-axis 3 times. So 1, 2, 3. But because this is continuing on infinitely up towards positive infinity, and this is continuing down towards negative infinity, it's never going to curve back up and touch that x-axis again. So the highest number of roots that a third degree polynomial can have is 3.
Mommy,
What?
how do I see your hand?
This is a camera.
The camera has to, you have to see your hand,
Mm-hmm.
I think.
Mm-hmm. Yeah, buddy.
And this is how you see it,
Mm-hmm.
that boxing
Yeah,
on the bottom.
yep. Can you go watch your movie?
Actually, now I need to play my tablet.
Okay. All right, so let's talk about a polynomial of degree n. So let me give you a couple of examples. Let's say I had a 5th degree polynomial.
Look, the movie's a halfway.
Okay, get your tablet, go sit down. That's Griffin. Okay, go sit down. You shut those doors. Okay. All right, so let's talk about a 5th degree polynomial. Right here, I saw that. We saw this right here. So this crosses 1, 2, 3, 4, 5 times. We just saw the parent graph of a 5th degree polynomial. This only crossed 1 time, but it could cross it as many as, like we just saw here, 5 times. So think about an nth degree polynomial, 6th degree, 7th degree, 8th degree. The most highest amount of times that it could have touch the x-axis or have those roots is going to be whatever that highest degree is. So this, a third degree polynomial has at most 3 roots. Nth degree polynomial has at most n roots. So this is asking part C, can a polynomial of degree n have fewer than n real roots? Let's think about that. And I want to relate it to the type of function you probably have the most experience with, which is a parabola. So this one we see only has a single root at the x-axis, but we also know of many cases where parabolas have 2. So could a parabola have less than 2 real roots? Yes, we've seen that here. Could a parabola have 0 real roots? And we've seen this plenty of times as well. If it doesn't touch the x-axis, then yeah, it could have 0. So the answer to this question, could a degree n polynomial have fewer than n real roots? It definitely can, as we've already seen. Okay, so moving on, let's turn the page. So look at these sketches up here. An example or problem 24. So we want to know the minimum possible degree. So the lowest possible degree, or remember, when I say degree, we're talking about the highest exponent. So for example, if I had a function or a polynomial like y equals x to the 7th plus x cubed minus 3x squared, this has degree 7. So that highest exponent is the degree of the function. So we want to know what is the lowest possible degree of this graph. And then afterwards, we're going to describe what happens to the y values of our function as x gets really, really large. So let's think about possible degrees. Could this be first degree? Think about what first degree means. That means to the first power. That would be linear. This is clearly not a linear function, not linear at all. So it couldn't be 1, and then we'll just work our way up. Could it be second degree? We know second degrees are parabolas. This is not a parabola. Third degree, could this be a third degree polynomial? Yeah, it could. So this is like a sideways S function. So this at the very least would have to be a third degree polynomial. And then we'll describe what happens as x values increase. So we're talking about as x values increase, which is get really, really large this way. What's the y value going to do? It's going to continue to approach positive infinity. So the y values, and instead of saying approach positive infinity, we can just use these symbols. So arrow means approaches, and then infinity. So the y values approach infinity as x values get really, really large. And then let's look at this one. So minimum degree. So this one, minimum degree, could it be first degree? Definitely not. It's not linear. Could it be second degree? Yes, it could. So this looks like a parabola. This could be minimum degree 2. And then let's talk about what happens as x values increase. What is the y value going to do? So as x gets really, really, really large, this is going to continue going down forever. So y values approach, so I can use the arrow, negative infinity. All right, moving on to this next one. We've got, we know this can't be first degree. We know it can't be second degree because that would be a parabola. We know it can't be third degree because third degree, the ends start in different spots. So this one, like we saw on a previous page, with both of these going up, looking kind of like a W, the very lowest degree this could have would be 4. And then as x approaches infinity, this y value is going to continue approaching infinity. So approaches infinity. And then lastly, we have this. So we know, again, it can't be first, can't be second, can't be third. Because it can't be third because of this number of turns. It has too many turns to be a third degree, like this one over here. So it can't be fourth because these are going in opposite directions. And we saw all of our fourth degree polynomials, the ends did the same thing. So this at the very least could be fifth degree. And as x approaches infinity, we see these y values approaching negative infinity. So approaches negative infinity. Okay. Okay, another thing I want to point out, I'm going to try and skip around here and get just to like the most important stuff. All right, so I want to jump down to problem 26. All right. So in this polynomial, in problem 26, we have p of x equals x minus 2 times x plus 5 squared. So we have two factors here, but this x plus 5 is squared. So it means that it's repeated. Or in other words, if I wrote out, instead of writing it as x plus 5 squared, you can think of it as x plus 5 times x plus 5. So that's what it means repeated. It's got that square with it. So that square right there means it's called a double root. It's a double root. And we want to know what effect that has on the graph. So let me type this function in here. So if I have x minus 2 times x plus 5 squared, and I look at the graph of this. So obviously this continues down more. So this is this one right here crossing through the x-axis. That's my x minus 2. And then x plus 5 squared gives us this x-intercept or root or 0 at -5. So what effect does that squared have on the graph? And that effect is that it's bouncing off of the graph right there. It's not crossing through it like it does here at 2. Instead, those double roots always behave like a parabola would, which should make sense when we think about parabolas. It's x plus or minus something squared in the graphing form. So those are always bouncing off of the x-intercept at those points. So these double roots bounce off. That's not an official math term. They bounce off. The technical term would be they deflect. So those roots deflect away. All right, so if we look, let's look at what third degree. So a cubic factor. In fact, I'm actually just going to leave this same one. I'm not going to use the example. If I change that to a third degree polynomial, or a third degree or cubic factor right there, let's see what that effect has. Okay, so this comes down and then it'll go back up here. So this third degree, it looks like the word I use for that, it kind of squiggles through. It kind of looks like the way the graph would if it was a cubic function, if I just ignored that half of the graph. So if it is a third degree root or factor, those squiggle through. And there's an official word for that too, but I like to use squiggle. Some people might use the word bend. It bends or squiggles. I don't know how to spell squiggle. Through the x-axis, the official term for that would be in a point of inflection. So that is inflection. You don't need to know these terms, inflection and deflection. I'm just telling you. So second degree roots bounce off. Third degree squiggle through or bend through. And then if it's a first degree, so like x minus 2. So with that one, that gave us this x-intercept of +2. This was first degree. And that just acts, it just cuts, whoops, can't see that now. Just cuts through it like a line would. So that just means it passes through just at an even, just slices right through it. So we were able to see about this, the behavior of some of these. And then this last question before the next page, what differences do you notice between the graphs of even degree polynomials and odd degree polynomials? So what I want you guys to hopefully pick up on is that all of our even graphs, so we had parabolas, we had things that looked like W's. We haven't looked at 6th degree polynomials, but we would see similar end behavior. If I had a 6th degree, it could look like this. What I want you guys to pick up on is that all of these even functions, their end behavior on the left and the right does the same thing. So either they are both pointing up or they're both pointing down. With odd degree, so like cubic, 5th degree, 7th degree, even linear functions to the 1st degree. So linear, those ends are doing opposite things. Cubic functions, those ends are doing opposite things. 5th degree ends are doing opposite things. So opposite end behavior for odd degree. And then same end behavior for even degree.
Mom,
Yeah.
on the dinner game, I killed a sheep.
Okay, I'm almost done, okay? All right, so flip over. I'm gonna finish up with this last problem on the next page. So there may be, just FYI, some homework problems that reference number 27 on the homework. Don't worry about those for now. I just wanna get you guys, like, again, the most important stuff here. So look down at example 30. And now that we've kind of figured out what the degree of each individual factor tells us about the behavior and what the zeros are, we can actually sketch pretty decent graphs of these without using a calculator at all. So there's 3 things we need to look at. What's the degree of the function? So we need to know degree. Whoops, degree. We need to know, is the leading coefficient positive or negative? So in this case, that in example A, it's negative. So lead coefficient. And then we also need to know what each of these factors is doing at the x-axis. So this is 3rd degree right here, because I have this x here, this factor here, and this factor here. So my 3 roots, remember roots are zeros or where it crosses the x-axis. So this factor of an x means it's got a 0 at 0 or a root at 0. X plus 1 means it's got a root at -1, and x minus 3 means it's got a root at +3. Then I need to know, where does it start and end? Well, this is a 3rd degree polynomial. So typically a 3rd degree polynomial would start down here and end up here. But this has a negative leading coefficient. So that means it's going to reverse. It's going to start up here in the top right and then end down here in the bottom, or sorry, start in the top left, end in the bottom right. And then we need to look at the exponent of each individual factor. So each of these individual factors is degree 1. So that means it's just going to cross right through the x-axis at each of these. So I know I'm starting up here, I'm ending down here. And then it's just going to cross through at each one. And then that's my sketch. Let's do the next one. So we've got, let's see, the degree. So this factor right here, x minus 1 squared, that double root, remember that double root, that counts for 2 degrees of this function. This next one, so that's 3, and then this next one, 4. So this is 4th degree polynomial. So it's even, which means my ends are going to do the same thing. So even degree, my zeros, so x minus 1 means I have a root at +1. X plus 2 means I've got a root at -2. And x minus 4 means I have a root at +4. Now I need to know, does my function start up here or down here? Well, 4th degree polynomials behave like 2nd degree polynomials. They either both start up or they both go down. My leading coefficient is positive. That means both of these are going to start, it's going to start and end going up to positive infinity, because even functions have the same end behavior, both pointing up or both pointing down. And then the other important thing for this is that x minus 1 is a double root. That means it's going to be bouncing off at 1 when I get to that. But since x plus 2, that is just a 1st degree root, that means it's going to cross through it. So I sketch that piece first. And then at 1, since that's a double root, it's going to come back up to it and then bounce off. And then 4, that's also 1st degree, so it's going to cut right through that. So that's how we can tell the behavior without grabbing our calculators at all. we can be sure it's going to cross through the x-axis at -2, bounce off at 1, and cross back through at 4. So there's some pretty cool stuff that we're able to do with these polynomials now that we have more knowledge about them. Okay, really quickly, this last one. So let's look at the degree here. So I have a cubic root here and a single first degree root here. So altogether, this is another 4th degree polynomial. I've got this root of -2 and this root of +4. Now we need to figure out where this graph starts and ends. It's a 4th degree polynomial. And my leading coefficient is just +1. So that means, again, they're both going to start up here. But this -2 right here, or this x + 2 cubed, that gave us the root of -2, that's going to, remember, squiggle through the way a 3rd degree polynomial would. So this is going to come down and kind of squiggle through right there. And then when I come back up through 4, since that's 1st degree, it's just going to cut right through right there, just like that. So the big takeaway from this section is these last few problems. If you've got this factored form, you guys should be able to tell me the degree of the function, and then what the roots of the function are and what happens at each root, whether or not it crosses through, bounces off, or squiggles through. So that's it for these. So your homework now will be to just do the 8.1.2 review and preview. And hopefully I'll see y'all very soon. Okay, bye.